Nearly 9 years ago, NASA deliberately flew a spacecraft into the atmosphere of Saturn and let it burn apart, ending a 13-year mission on purpose, specifically to avoid the small chance that the aging probe might one day crash into one of Saturn's icy moons and contaminate it with hardy Earth microbes still clinging to its hull. That single decision tells you almost everything you need to know about how seriously NASA's own scientists have taken the possibility that a small, unassuming moon of Saturn called Enceladus might actually be capable of supporting life. And in the years since that deliberate sacrificial ending, researchers have kept going back to the data that spacecraft, Cassini, gathered during its actual working years, finding new answers buried in old readings that the original instruments were never sophisticated enough to fully decode. In November 2025, one of those renewed analyses delivered its most significant result yet: definitive proof that complex organic molecules detected in Enceladus's icy plumes weren't simply passing through space. They were actually manufactured inside the moon's own hidden ocean, the direct product of active chemistry happening right now in liquid water, sealed beneath miles of ice. This is the real story of what NASA has actually found inside Enceladus, why the case for a genuinely habitable ocean beyond Earth keeps getting stronger with each new pass through this old data, and why a growing chorus of scientists is now pushing hard for a mission built specifically to go back and look for life directly. I'm your host, and this is your channel. If you want the real science behind the biggest discoveries in space, subscribe now, because we're just getting started. To understand why Enceladus occupies such a genuinely unique position in the search for life beyond Earth, you first have to understand exactly what makes this specific moon so different from almost everywhere else astronomers have looked. Enceladus is small, just over 300 miles across, easily overlooked next to Saturn's much larger, more famous moon Titan. But in 2005, NASA's Cassini spacecraft, then in the middle of its long tour of the Saturn system, captured something nobody had expected from a world this small and this cold: massive plumes of water vapor and ice erupting directly out of cracks near the moon's south pole, shooting hundreds of miles into space. Those cracks, informally nicknamed tiger stripes because of their distinctive parallel, striped appearance, turned out to be venting material from something genuinely remarkable, hidden beneath Enceladus's icy crust. An entire global ocean of liquid water, sealed away under miles of ice, kept liquid not by sunlight, which barely reaches this far from the sun at all, but by tidal heating, the constant flexing and internal friction generated as Saturn's powerful gravity continuously stretches and squeezes the moon during its orbit. That discovery alone would have made Enceladus scientifically interesting. What made it something closer to extraordinary was what happened next. Because those plumes were actively spraying material from the ocean directly into space, Cassini didn't need to land on Enceladus or drill through its ice to actually sample what was inside that hidden ocean. It could simply fly directly through the plume itself and let its instruments taste the ocean's own chemistry as it passed through, ice grains and vapor striking the spacecraft's detectors at high speed, revealing the actual composition of an alien ocean without ever needing to physically touch the moon's surface at all. Cassini did exactly that repeatedly across the following years, using an instrument called the Cosmic Dust Analyzer, specifically designed to examine the composition of tiny particles striking the spacecraft. And the results, even from those first flybys, were genuinely striking. As early as 2006, researchers analyzing this data confirmed that Enceladus's plumes contained organic molecules, carbon-based compounds that, on Earth, form the basic chemical foundation for every living thing. That initial finding was significant, but it was also, in an important sense, incomplete, because the instruments available at the time weren't sophisticated enough to fully identify exactly which specific organic molecules were actually present, or to definitively confirm whether those molecules had genuinely originated inside the ocean itself, rather than forming through some other, less biologically interesting process elsewhere in the moon's environment. The mission that finally began resolving those remaining uncertainties came in June 2023, when a research team led by Frank Postberg, a planetary scientist at Freie Universität Berlin, published findings in the journal Nature, identifying something that had never before been detected in any ocean beyond Earth: phosphorus. Postberg's team focused specifically on data Cassini had gathered not from flying directly through Enceladus's plume itself, but from passing through Saturn's E-ring, a faint, diffuse ring of icy particles fed continuously by material escaping from Enceladus's plumes over time. Because Cassini had flown through this broader ring far more often than it had flown through the concentrated plume directly, the E-ring data gave researchers a much larger sample of individual ice grains to examine in detail. Within that expanded dataset, the team discovered high concentrations of sodium phosphates, chemically bound molecules containing sodium, oxygen, hydrogen, and phosphorus together. Postberg explained why the specific element mattered so much to the broader search for extraterrestrial life. Enceladus's ocean was already known to be rich in a variety of organic compounds, he noted, but this new result revealed the clear chemical signature of substantial amounts of phosphorus salts inside the icy particles being ejected into space by the moon's plume, marking the first time this specific essential element had been discovered in any ocean beyond our own planet. Phosphorus matters enormously to biology because it's a genuinely essential building block for life as we understand it here on Earth, a critical component of DNA, RNA, cell membranes, and the molecule cells used to store and transfer energy. And it happens to be the least abundant of the essential elements required for these core biological processes, making its detection considerably more significant than confirming the presence of more common elements would have been. Follow-up laboratory work conducted by the team's European and Japanese collaborators went further, demonstrating that Enceladus's ocean likely contains phosphorus in various water-soluble phosphate forms at concentrations at least 100 times greater than what's found throughout Earth's own oceans, a genuinely striking abundance that, if anything, suggests Enceladus's ocean may actually be more chemically favorable for the specific processes life depends on than our own planet's oceans are. That 2023 phosphorus discovery set the stage for the far more comprehensive finding that followed roughly 2.5 years later. Published on October 1st, 2025 in the journal Nature Astronomy, a research team led by Nozer Khawaja returned to Cassini's archival data once more, this time applying newly refined analytical techniques specifically designed to extract considerably more detail from the same underlying data set than earlier analyses had been capable of achieving. Khawaja explained the basic premise behind this renewed effort directly. Cassini had been detecting samples from Enceladus constantly throughout its mission, every time it flew through Saturn's E-ring, but making sense of exactly what those samples contained required analytical tools and experimental techniques that, in some cases, simply hadn't existed yet when the original data was first collected. The team's approach involved painstaking laboratory experimentation here on Earth, systematically testing how the specific speed at which an ice grain strikes a detector affects the resulting chemical signal that instrument records. This mattered enormously because Cassini's cosmic dust analyzer had recorded ice grains striking it at a wide range of different velocities during different flybys, and without properly accounting for how impact speed itself distorts or alters the raw chemical signal being measured, researchers risked either missing genuine chemical signatures entirely or misidentifying what specific molecules were actually present. By running exhaustive experiments, recreating these different impact conditions in a laboratory setting, and carefully modeling how each different impact speed would be expected to alter the resulting data, the team was finally able to go back through Cassini's real historical flyby data with considerably more analytical precision than had ever been applied to it before. The results confirmed something genuinely important for establishing exactly where these organic molecules had actually originated. The research team successfully demonstrated that certain organic compounds, ones previously identified only in scattered, more ambiguous detections within Saturn's broader E-ring, were also present in meaningfully high concentrations within freshly ejected ice, sampled directly from the plume erupting out of the cracks at Enceladus's south pole. That specific match mattered because it allowed the team to establish a genuine, confirmed chemical link connecting material found broadly scattered throughout the E-ring back to material freshly emerging directly from Enceladus's own subsurface ocean, effectively proving that these organic molecules truly originated inside the ocean itself, rather than forming through some separate, unrelated process happening only after the material had already been ejected into space. Beyond simply confirming the oceanic origin of previously known organic compounds, Khawaja's team also identified entirely new molecules within Enceladus's plumes that had never been documented there before, expanding the moon's known chemical inventory considerably. That expanded inventory included a variety of molecular fragments that, here on Earth, are directly involved in chemical reaction chains eventually leading to the formation of larger, more biologically significant compounds, the kind of stepping stone chemistry that, on our own planet, sits somewhere along the pathway between simple, basic chemistry and the more complex molecular machinery genuinely characteristic of living systems. The research team described this specific finding as a clear sign that genuinely complex chemical reactions are actively taking place within Enceladus's underground ocean right now, with at least some of these ongoing reactions potentially forming part of longer chains that could eventually lead to even more complex and more directly biologically relevant molecules than anything detected so far. It's worth being genuinely precise and honest about exactly what this discovery does and does not actually demonstrate, because that precision matters enormously here. And it's exactly the kind of distinction serious researchers themselves have been careful to draw. Finding organic molecules, even genuinely complex ones, inside Enceladus's ocean is not the same thing as finding life itself, or even finding definitive proof that life could survive there. Organic molecules of this general kind can form through entirely non-biological, purely chemical processes as well, and confirming their presence establishes that the basic chemical raw materials life would need are genuinely available within Enceladus's ocean, without establishing that those raw materials have actually been assembled into anything resembling a living organism. What this finding does represent is a genuine incremental strengthening of the overall case that Enceladus's ocean could plausibly support life if the right additional conditions and processes happen to be present, moving the broader scientific conversation from establishing basic habitability, whether the ocean has liquid water and energy at all, toward examining increasingly sophisticated chemistry that starts to resemble the kind of processes biology actually depends on. This organic chemistry finding didn't arrive in isolation either, and it's worth understanding how it connects to a separate, complementary discovery published just weeks later that addresses a different, equally important question about Enceladus's habitability, not simply what chemistry exists in the ocean, but whether that ocean can actually remain liquid and hospitable over long stretches of geological time. On November 9, 2025, researchers published findings revealing something genuinely surprising about how Enceladus generates and distributes internal heat. Using Cassini's own archival data, the team found that the moon releases significant thermal energy from both its south pole, where the famous plumes and tiger stripes are located, and in a considerably more surprising finding, from its north pole as well, a region that hadn't previously been recognized as a significant source of the moon's internal heat. That specific finding matters because it addresses a genuine, previously nagging concern among researchers studying Enceladus's long-term habitability. If a moon this small were only generating substantial internal heat at one specific location, some models suggested the underlying ocean itself might eventually become unstable over sufficiently long timescales, potentially freezing solid in some regions while remaining liquid elsewhere, rather than functioning as the kind of genuinely global, long-lasting body of liquid water life would most plausibly need to persist and evolve over meaningful stretches of time. Finding that Enceladus generates and releases significant heat from both poles suggests a more balanced, more genuinely global internal heating process, one considerably more consistent with the ocean remaining stable, liquid, and geologically active, across the kind of extended timescales that matter for the emergence and potential persistence of life, rather than representing some comparatively brief, geologically temporary phase in the moon's history. Taken together, this accumulating body of research, the 2023 phosphorus discovery, the 2025 confirmation of ocean-derived complex organic chemistry, and the parallel finding regarding balanced dual-pole heat flow supporting long-term ocean stability, has meaningfully strengthened the scientific case that Enceladus represents one of the most genuinely promising locations in our entire solar system to search for signs of extraterrestrial life, a case built entirely on real physical, chemical evidence gathered directly from the ocean itself, rather than theoretical speculation about what conditions might exist there. It's worth being clear-eyed and balanced about the genuine scientific caution that continues to surround this overall body of research as well, because responsible science requires holding both the excitement and the uncertainty in view simultaneously. Not every researcher studying Enceladus's plumes has reached identical conclusions about exactly what the accumulated evidence actually implies. Some published research, including a study released in September 2025, has raised genuine, carefully argued questions about whether certain aspects of the plume's chemistry might potentially be misleading researchers in specific ways, cautioning that the moon's plumes, while genuinely revealing, may not always provide a perfectly clean, unambiguous window into every aspect of the ocean's true underlying chemistry and conditions. That kind of internal scientific debate isn't a sign of a weak or unreliable body of research. It's exactly the kind of rigorous, self-correcting process that distinguishes credible science from a rush to premature, overconfident conclusions, and researchers across the field have generally treated it as a genuine, constructive part of continuing to refine and stress-test the overall picture, rather than as evidence undermining the core, repeatedly confirmed findings themselves. This accumulating, increasingly detailed body of evidence has directly fueled growing momentum within the scientific community for a genuinely dedicated follow-up mission to Enceladus, one specifically designed to search for signs of life directly, rather than relying on archival data gathered by a spacecraft that was never originally built with that specific goal in mind. October 2025. Organic chemistry findings were explicitly described by the research team as further strengthening the case for a dedicated European Space Agency mission specifically intended to orbit and potentially land on Enceladus, a mission that does not yet exist, but that a growing body of researchers argue is increasingly well justified by exactly this kind of accumulating chemical evidence. It's worth understanding a bit about what a genuinely dedicated future mission to Enceladus might actually be capable of accomplishing, because it helps illustrate exactly how much more remains to be learned beyond what Cassini's original, more general-purpose instruments were ever designed to detect. Cassini was never built as a dedicated astrobiology mission specifically targeting Enceladus. It was a broader, general-purpose Saturn system explorer, studying the planet itself, its rings, and its many moons collectively, with its instruments optimized accordingly across a wide range of scientific goals rather than specifically maximized for detecting the most subtle, most biologically significant chemical signatures a hidden ocean might contain. A future mission built specifically around Enceladus, carrying instruments purpose-designed to search for genuinely more advanced biosignatures, specific chemical patterns, molecular structures, or isotopic ratios that would provide much stronger, more direct evidence of active biological processes, rather than simply the more basic chemical building blocks life would require, could plausibly answer questions that Cassini's own general-purpose instruments were never sensitive enough or specifically designed to address at all. Scientific American's own coverage of the November 2025 organic chemistry findings captured the genuine, carefully balanced state of excitement and remaining uncertainty that characterizes this entire field of research. The discovery, the publication noted, bolsters the case for follow-up missions specifically designed to search for direct signs of life within this genuinely enigmatic moon, language that reflects real, substantive, scientific progress while still being honest, that a dedicated direct search for life itself, rather than simply its chemical prerequisites, remains a future goal, rather than something Cassini's archival data alone has already accomplished. So here's where this genuinely, honestly stands, based entirely on peer-reviewed research published in Nature and Nature Astronomy, and the direct, on-the-record statements of the scientists who conducted this work. Enceladus, a small icy moon of Saturn that nobody expected to be geologically active at all before Cassini's cameras first spotted its plumes in 2005, has revealed, through nearly 2 decades of patient, increasingly sophisticated analysis of data gathered by a spacecraft that ended its own mission on purpose to protect this exact moon from contamination. A subsurface ocean containing phosphorus at concentrations far exceeding Earth's own oceans, complex organic molecules confirmed to originate from active chemistry happening directly within that ocean, and evidence of balanced dual-pole heat flow suggesting that ocean has likely remained stable and liquid across genuinely long stretches of geological time. None of this constitutes direct evidence of life itself. All of it represents genuine, carefully verified confirmation that the basic chemical and physical conditions life would require are demonstrably present, in real, measured quantities, inside an ocean beyond Earth for the first time in the history of human exploration. That is not manufactured drama, built around an exaggerated headline. That is the honest, carefully documented, genuinely significant scientific legacy of a spacecraft that keeps teaching us new things about a moon its own instruments were never specifically built to fully understand, nearly a decade after that spacecraft deliberately burned apart in Saturn's atmosphere to keep this exact possibility genuinely open. If this kind of story is what you come here for, one grounded in exactly what NASA's own researchers measured, confirmed, and directly explained, rather than exaggeration, hit subscribe and turn on notifications, because there's clearly more waiting to be discovered inside this same archival dataset, and potentially far more waiting inside Enceladus' ocean itself. Drop a comment telling me whether you think a dedicated mission to Enceladus will actually get funded and built in your lifetime, and share this with someone who still thinks the search for life beyond Earth means looking for something living on a planet's surface, rather than hidden beneath miles of ice on one of its smaller, quieter moons.